Guess what? Great news. There's a shortcut to use the definition of a derivative to find the slope of a tangent line. And today I'm going to show you what that shortcut is. I made a video recently where I did it the long way using the real definition of a derivative, but man, that's a pain in the butt. So today I'm going to show you the shortcut of how you can use a little bit of a simpler definition of a derivative to find the slope of a tangent at a specific point. And we're going to be doing this using the same function that I did in my other video, which is a both fraction and square root function. So it's a pretty complicated example, but I'm going to show you that it's really not that difficult with this shortcut. So hopefully that'll save you a ton of frustration later on. So let's go ahead and just jump on into how to do it. So before we jump into this problem, I quickly want to mention I have done this problem using the expanded version of the definition of a derivative, but now I want to show you the shortcut of how you can do this exact same problem using this alternate version of the definition of a derivative at a specific point. And keep in mind, both of these formulas are on my Calculus 1 study guide that I have. You can go get that for free right away, right now. If you just go down to the link in the description, it'll take you over to a page where you can put in your email and I'll send you a PDF of that study guide right now. So go ahead, push pause, go grab that real quick, come back here and I'll show you how to use this formula. But what we're going to do is we're going to find the slope of the tangent to the curve y equals 1 over the square root of x at the point where x equals a. And like I said, this is kind of the shortcut formula of how you can find the slope of a curve at a given point if you know that point. In this case, we have some just generic x equals a, but the idea is the same. If you were to be given an actual value for a, you could just plug that into our answer for a and figure out what the slope at that point is. So as we work through this, you're going to notice that the process that we're going to go through is actually going to be pretty similar to that other expanded version of this problem that I already did, but the simplification and the arithmetic that we have to go through is going to be quite a bit easier and shorter. So that's why I wanted to show you this shortcut. And all we're really going to do now is use our function this is going to be f of x, 1 over the square root of x. And we're going to use this function here in this formula here. So really, we already know our f of x is 1 over root x. The only other piece we kind of need to figure out is f of a. Well, to figure that out, all you have to do is go to your function f of x, and wherever you see an x, just replace it with an a, whatever's in the parentheses here. So that just gives us 1 over the square root of a. So if we just take these two pieces here now and plug them into this formula, we'll be able to use that to find the derivative of our function at some a value, which, keep in mind, derivative just represents slope. So if we're finding the derivative of f at a, that is exactly what the slope of our tangent at x equals a means. So we're just going to be finding the limit as x goes to a of f of x, which is 1 over root x, minus f of a, which is 1 over root a, all over x minus a. So typically when you're trying to evaluate a limit like this, the easiest place to start, and a lot of times it doesn't work, so don't think that this is how you can always solve a limit, because it's not true. But it's a good starting point, a good jumping off point, is to whatever your x is approaching, just plug that in for x and see what you get. Unfortunately, if you do that in this case, what you're going to find is that we get 0 on the denominator down here, because we're going to get a minus a, which is 0. Unfortunately, dividing by 0 is against the rules of math. You're breaking math basically by doing that. It doesn't actually make any sense. So we need to think of another strategy. Usually that strategy is going to be manipulating your numerator so that it also has an x minus a term in it somewhere that can cancel out with our x minus a on the denominator, and then trying to just plug in a for x at that point. So that's kind of our end goal here, is to look for an x minus a somewhere in the numerator. Well, we do have an x, we do have a minus, and we do have an a, but it's not just x minus a in a single term. So we need to do some manipulation here. Usually when you have some sort of square root term minus or plus some sort of other square root term, the best place to start is by multiplying the top and the bottom of this fraction by the opposite of whatever's up here. So in this case, we have 1 over the square root of x minus 1 over the square root of a. We want to multiply it by 1 over the square root of x plus 1 over the square root of a. If we had a plus here before, we would just put a minus here. But what you want to keep in mind is whatever you do to the top of a fraction, you also have to do to the bottom of that fraction, or else you're changing its value and it's no longer equal. So the great thing about this is what this is doing up here on the top is this is basically doing the reverse of what difference of squares does. Difference of squares says that if you have some squared term minus some other squared term, you can factor that out into the square root of c squared, which is just c, minus d times c plus d. So here we're doing the opposite. We have something minus something times that first thing plus that second thing, just like this. So we can kind of go in the reverse order and write that instead as our first thing squared minus our second thing squared. So we can write it as 1 over root x squared minus 1 over root a squared. Well, all that does is it creates 1 over x instead of 1 over root x, and 1 over a instead of 1 over root a. And then on our denominator down here, we're gonna do x minus a times all this here. You could FOIL this out, but that's really just gonna make things more complicated. Remember, our goal is to get an x minus a term both in the top and the bottom so that they can cancel out. We don't wanna FOIL it out because it's gonna be harder to cancel that x minus a term out. We're just gonna have to undo that later. So on the bottom, we're just gonna have x minus a times 1 over root x plus 1 over root a. So now what you may notice is we have a fraction. Obviously this whole big thing is a fraction, but within the numerator and the denominator we have more fractions, which is kind of a mess. You don't really like fractions within fractions. So what we can do is, again, kind of manipulate our numerator to just get one big fraction, and then we can kind of condense this whole thing down into a neater fraction. So to do that, we need to combine these terms into one single term, which means they need a common denominator. So we can multiply this by the denominator of the other on the top and the bottom, and we can multiply this fraction by the denominator of the first one, both again on the top and the bottom. So doing that is going to give us a times 1, which is a, over a times x. This fraction is also going to be over a times x. So what that means is we're going to be able to just do the numerator of this one minus the numerator of this one. 1 times x is x, so a minus x over a times x. And that is our entire numerator now. And again, our denominator is just going to stay the same. And now what you can keep in mind is that doing this thing divided by this thing here is the same as doing this times the reciprocal of this. So in general, dividing by something is the same as multiplying by its reciprocal. A reciprocal is just 1 over this. So doing this fraction here of a minus x over a times x divided by all this is actually the same as doing a minus x over a times x times 1 over all of this. So now remember, our goal was to get an x minus a on the top and the bottom so that they can cancel. Unfortunately right now we have an a minus x, not x minus a, which seems like maybe we screwed up. But actually we can very easily convert a minus x into x minus a by multiplying it by -1. So if we multiply the top and the bottom of this fraction by -1, we're again not changing its value, but what we can do then is make the numerator be just x minus a. X minus a times 1 is just x minus a. And then with the negative on the denominator, we can apply that to a different term than this one. So maybe we could just put negative ax in front there. And that is still equivalent, because if you were to distribute all these fractions out, you would still end up with the same thing. The denominator itself would be different, but when you do this numerator divided by this whole denominator, it would still be the same, even though we've now switched those and then made the negative ax out here. So we've taken care of that, multiplying the top and bottom by -1. So now we just have this one single fraction, which is basically x minus a over the product of these other three terms. Well, now we have the x minus a on the top and the x minus a on the bottom that we wanted. So we can just cancel those out, and that's just going to give us the limit as x goes to a of 1 Remember, whenever you cancel something that is the entire numerator, you need to put a 1 as a placeholder. Of negative ax times 1 over root x plus 1 over root a. Well, now, what happens if we just plug in a for x, like I initially suggested we might be able to do? If we do that, we're just going to get still 1 on the numerator. Our denominator is just going to become negative a times a, which is a squared, times 1 over the square root of a plus 1 over the square root of a, which is just 2 over the square root of a. And remember, this was equal to f prime of a back at the very beginning up here. And now we can simplify this. So this denominator down here having a squared times a square root of a on the denominator. Square root of a is the same as a to the 1/2. Having a squared divided by a to the 1/2 is just going to give us a to the 3/2 on our denominator. And that's still going to be multiplied by 2, and we're going to have a negative. So this can again be kind of simplified to negative 1/2 a to the negative 3/2 power. So this is exactly what we got in my other video where I did this same problem using the long-winded definition of a derivative. And this is kind of a similar process, but the arithmetic I do think is a little bit simpler. So we can see that this is going to be the slope of the tangent to this curve y equals 1 over root x if we have some given a value. And what we could do is just plug in that a value into either of these equations to figure out that actual slope. Not too bad, right? Well, hopefully you found this video helpful. If you did, please be sure to hit that like button down below. Subscribe to my channel as well while you're down there and hit that bell icon so you see all my videos. And I'll make sure that we keep crushing it all term long. If you want a little more practice with tangent line equations, go ahead and click on one of those videos over there. Thanks and see you next time.